Okay, so let's do some thought experiments in DC before we make the leap into AC. We know that generators produce alternating currents, but for the battery, just as a recap, with three elements that are interesting, let's say the capacitor, and these will be I versus T, the inductor, and the resistor. And they're all in a situation where they're just connected to a battery, right? So black box, I'll put a big X through it. This is a mystery component that's unknown. Right at time equals 0, we turn this on, and you know the capacitor will start really fast, absorbing the current, or allowing the current, and then it'll die off. And the inductor will slowly build up until it reaches equilibrium. And what happens to the resistor? It doesn't really care. It's ready to party immediately, right? So it's on and it's always on. So these are interesting behaviors that we get for the DC case. I want to ask ourselves what happens if we drive these things at some kind of frequency. So instead of being on a battery, now I'll connect them to maybe an AC voltage. Remember, that comes out, it pushes the voltage and current one way, and then it pulls it back and it oscillates back and forth. So we should ask ourselves, what kind of a current response should I expect from the capacitor, in this case, at different frequencies? Let's say the frequency is low, which actually, this is technically a frequency of 0, isn't it? The period is infinity. You have all the time in the world between cycles because there is no second cycle for these things to come to equilibrium and tell us what they want to do. So what would the results be in, say, I'll make my frequency 0, which is the DC case, and I want to ask about the current for the capacitor, the inductor, and the resistor. For the capacitor, what do you expect? If the frequency is 0 or low, let's just say not 0, but towards 0, right? Low frequency. There's a lot of time between cycles. We'll see the current come into the capacitor a little bit, right? But it'll totally fill up and then choke that flow off. And we'll see it be pulled out, and there will be a little bit of flow back and forth, but not much, because the capacitor is always having time to bleed it off slowly and to choke off the current. So I don't expect to see very much current here. Okay, the current never really has a chance to blossom because it's always getting choked out by the full capacitor, and that kills it for the whole circuit. What about the inductor? Well, it needs a lot of time in between cycles, right? It needs a lot of time to adapt to the changing current. So if the current's changing very slowly over a long period with a low frequency, the inductor has plenty of time to warm up and allow that current to go through. So this actually kind of responds well to a low frequency. And then the resistor, whatever. It doesn't really care, right? It's instantly on or off. So whether it goes fast or slow, the resistor doesn't really care. What if we turn the frequency up? Close to infinity, really super high. In that case, here's the capacitor, and you're going to throw current onto it and then yank it off really quick before the capacitor ever really has a chance to completely fill. So you're always seeing the current flowing in and out really quickly without a whole lot of interference from the capacitor, or not a whole lot of, I don't know, we can say it's not reacting well or it's not resisting much. So the capacitor is totally fine with that and will have a high current. The inductor, on the other hand, you know from Faraday's law, it doesn't like to see changes, right? So the faster you drive this, the more the inductor hates it and the more it's going to fight back because it needs a lot of time to adapt. So the faster it's moving, the harder it's pushing back. And then, of course, here's a resistor that's like, yes, right, whatever it's doing. This is so uninteresting, we'll throw the resistor out. But these are super interesting, the capacitor and inductance behavior in response to the circuit. So let's summarize these in maybe a better table. Let's say the frequency, and then this will be the current. If the frequency is low versus high. For the capacitor, the current would be low. For the inductor, it would be high. Let's see, L and C. And for this, it'll be high. For this, it'll be low. So we're familiar with kind of modeling these in special cases, right? So let's say if this is our circuit, we'll make the generator connected to the capacitor. And in this case, we'll make the generator, make the generator connected to the inductor. Let's say here the frequency is 0. What does this circuit look like? Well, if the frequency is close to 0, the capacitor never really has time to allow this to happen. It looks like a broken wire. But the inductor looks like a short circuit. So these are kind of our models at low and high behavior. Over here, as the frequency goes to infinity, we're getting much better response from the capacitor until ultimately it looks like just a wire. And then here's your inductor. It looks broken. So these are kind of your extreme cases that we should be thinking about. Other things that you might hear these called, depending on how they're hooked up in series or parallel. In a series case, the capacitor would be called a high-pass filter. And that means if you have a signal or something on the line and you want to filter stuff out, the capacitor is really keen to listen to fast-moving frequencies or, high frequencies. So anything that's low, like a background hum or anything like that, it doesn't have a chance to get through the circuit. The capacitor kills it off. But the highly variable parts, that part is allowed to pass through. So it's called a high-pass filter. In the inductor, it's the opposite, right? If you don't want high frequency or really sudden changes, then the inductor catches those and blocks them out. But it does allow low frequency changes through. So this is called a low pass filter, and a good place I can think of one is, I think it's called the ballast in fluorescent lighting. So the instant you flip the switch, you get a really sudden spike or a surge. Well, the inductor is, by its own nature, doesn't like that and cuts it out. So in some ways, I guess you could build a very crude surge protector out of just putting an inductor in series with the rest of the circuit. So it's in here designed to kind of catches high frequencies or catches low frequencies and allows the other two through. And if it was in parallel, you'd have opposite rules because of the way parallel works. Okay. So I think maybe we should think about what is happening in the circuit. You mean to be telling me that by using a capacitor or an inductor, depending on the frequency, they can affect the current? That sounds an awful lot like what a resistor does. And it's true. In some way, a resistor moderates the current flow according to V equals IR, right? We know that. But in some strange way, a capacitor and an inductor also affect the current flow. So in a way, they kind of have a resistance. I don't want to call them a resistance because resistance is literally crashing into other atoms and stuff in the way. So maybe we should think about a different term that means about the same thing. Let's say that they react. L and C do react to different frequencies differently. So that's interesting. Let's say Ohm's law still applies. So we have V equals I. We need a new symbol, right? So let's just call it C. Ask ourselves, if we wanted to talk about, say, the capacitive reactance, how would it depend on the current flow? We know that if the current, or if the frequency goes up, then the current in the system goes, well, up, right? Faster flow, or faster sequencing, less time, the capacitor keeps flowing. Okay. What's that mean about the reactance? in V equals IR, if I get more current, then I must have less reactance to it, right? So it's not doing much. So we'll say the reactance on the capacitor goes down. I need to invent some kind of a formula that helps me understand that. And that one is not obvious. Maybe I should have done the inductor first. If we have here, the frequency is going up. This is capacitor. Okay. If for the inductor, we'll let the frequency rise. What do we know about the current? It's falling. And what's that mean about the inductive reactance? It must also be going up, according to this law, right? One goes down, the other one goes up for the same driving frequency. Well, I need some kind of a relationship between the frequency and the inductance that helps me kind of model XL. I suspect that it'll depend on the component, but it's also really important, where does the frequency come in? It must be in the numerator, right? Because if I want this to go up and this to go up together, I need that in the numerator. So I'm going to take a guess and say that this is probably, hopefully, a reactance. And if it's going to apply an Ohm's law, it should have units of ohms, right? Let's try this. Frequency is rad per second, but we know radians are kind of easily forgettable. And then the inductance is an ohm times a second. What do you know? It does come out in terms of ohms. I need some kind of an inverse relationship here for the capacitive reactance. So for that one, I guess whatever's going on probably is happening in the denominator. I know that has to be on the bottom. And I'll just take a guess and say that C is also on the bottom. So we should try it. I get 1 over what? 1 over seconds. Actually rads per second, but remember I ignored them. And then times a farad. Well, that's, I guess 1 over seconds is actually on the top. So that's seconds per farad. Equals seconds per, I guess we had what? Coulombs per volt. This is a volt per coulomb per second, which is a volt per amp, which is, by Ohm's law, is also an ohm. So this stuff looks interesting. I can find currents in an AC alternating system given a certain voltage based on, well, how does a capacitor and inductor behave in this kind of a circuit by reacting in some way to the frequency. So this is super interesting. By now you should already know RMS and peak in these circuits. Whenever you want to do these kinds of equations, it doesn't really matter. If you start with an RMS voltage, you'll get an RMS current, and you can use XL or XC or R to figure that out. If you started out in peak, that's fine too. Your results will be in peak. And really, the reactances do not care. This will help us find amplitude, or we can scale the amplitude either by its peak value or its RMS value, because it's all the same in these formulas. So that's what the reactances are. They're kind of like a resistance, but not quite. And that's because, you know, it's fundamentally not a resistance, but it seems to behave like one, and it reacts to the frequencies differently.